The first one is Dr. Riccardo Taormina. I know Riccardo for some years. We worked together with HydroLab in graph-related research, and he's going to tell more about meta models for water distribution networks. I'll stop here with the introduction because we are already late, so go ahead.
Yeah, I really didn't want to speed up this talk and do it like slowly, but it's not going to be the case, I guess. So
you can cut with the questions.
Yeah. Well, thanks, Elvin, for the introduction. So indeed, yeah, it worked. Good.
Yeah, perfect.
So yes, I'm the co-director of HydroLab along with him, and I work in this faculty in the Department of Water Management. And we cover different things in terms of applications in HydroLab, but water distribution networks is one of them. Okay. And today's talk, actually, we have three of them, although they're going to be a little bit shorter. So you can see the first talk is going to be on graph neural networks to build meta models for water distribution networks, which is a type of water network. Then Alex is going to have another talk in which we also mentions transferable meta models, but for sewers, urban drainage. And then lastly, we go back to water distribution. A different application now is not going to be graph neural networks, but it's going to be complex graph theory along with the machine learning methods to solve an important problem in water distribution networks again. Now, the first part should be like a generic introduction to the topic, because I guess the audience is kind of very varied. So yes, urban water networks and why we want to use graph machine learning. That's the first part of the talk. So let me give you some context. We are in the urban water cycle. Okay, what does this mean? This affects everyday's life, including, bringing water to firefighters when they need to actually extinguish a fire, which was not the case today. But what you have, usually you have a source of water, such in this case, it could be a river, could be a lake. In some part of the world is actually the sea itself with desalination plants. It can be the groundwater. So we have this water body, the source of fresh water somehow, and we found, from this, let's say, river in this case, and then we have water that needs to be treated to become potable, drinkable, and then it can be sent to usually like cities, via transmission pipelines. And then we have our city here that you can see, and we need, of course, this water to do everything essentially, for our households, for our, industrial processes, commercial, anything, we of course, it's needless to say, we really depend on drinking water. Of course, we consume this water, this becomes wastewater, or, we need to get rid of this wastewater and bring it back to the environment. But of course, we need to treat it first with another type of treatment process, wastewater treatment plants, and then we can release them into the, let's say, the same river, if you will, hopefully downstream, so you don't have to drink, what you just treated. And that sort of closes the cycle. We need an extra component, though, because, especially in the Netherlands, we have a lot of rainfall, right? So this is, again, water that, falls on our streets, on our roads, on our buildings. And again, it gets polluted because there is a lot of pollution also in the environment around us. I'm pretty sure you know about this, and needs to be treated as well. And ideally, it needs to then be, shared back with the environment with a concentration of whatever pollutant or pathogen are low enough for safety reasons. Okay. Now, this is all the urban water cycle, and that's already a lot. But when we talk about networks, we literally focus on this part alone. Okay, urban areas. Why? Because, okay, let's say we have this water treatment plant, we have drinking water, this water comes to our city, and then is distributed using a network. It's not done in a, let's say, point-to-point way, because it would be very inefficient. And this is the same as power distribution, road networks, telecommunication. Indeed, we have a network. And when we talk about delivering drinking water, we have a water distribution network or a water distribution system. So we want to deliver water with high quality to as many people as possible, of course, and with sufficient pressure. It means that you open the tap and the water comes out, okay? So it's not just the quality of the water, it's the quantity, is the energy linked to the water, because pressure is, of course, related to energy. And from the sources to any type of user, residential, commercial, industrial, also if you can think sometimes farms, and so on and so forth. So this is the first network type of urban water networks. This is like the light side of the force, some people call it, because then we have the dark side of the force, which is, sewage. Okay, so this is everything that I mentioned when you close the cycle, right? So you use this water, you produce wastewater, and for sanitation reason, you need to take this wastewater away from cities, of course, right? And that's why it's called also the dark side of water networks. But we also mentioned stormwater again, because we have rainfall. Rainfall washes off these pollutants. We want to avoid sanitary problems also related to that. We want to avoid situations of flooding. So we need to take also this water away. We collect it first using sewers, and then we take it away from the urban areas. Okay. Now, sometimes, especially in places like the Netherlands, you have these two functions. So the wastewater or sanitary sewer and the stormwater sewer connected. We have slightly bigger pipes. They're called like combined sewer systems, mainly because the Netherlands, for instance, is highly densely populated. So it's actually quite impossible sometimes to have two pipes next to each other. You only want to have one. And that's why, if you're in the field, more often than not, you also hear the term combined sewer systems. Now, regardless of the networks that we're talking about, these are physical networks, okay? I don't know your field, but most, I would say, or a huge part of graph and data related application deal with non-physical networks. So here it's pretty much different. For many reasons, I'm going to list a few. Our node and edge features actually do have physical meaning, these attributes, okay? So pipe diameters have a physical meaning, okay? Flow rates, the amount of water flowing into a pipe, has physical meaning. Same goes for the fact that we have physical system, they have to obey physical laws, right? As such, we need to follow the law of fluid dynamics for a water network. These laws are very different if you think about a social network where, it's not physical, user behavior, for instance, social norms, you cannot call them physical, right? It's still very important laws, but maybe less understood, but big difference. Another big difference is, for instance, consideration about spatial relationship. Literally, if you have a pipe which is 1,000, a kilometer long, there's going to be much more energy lost carrying, water from point A to point B. In the case, this was like 10 times smaller, right? So there are physical implications. The spatial relationship is not the same, for instance, for social network, because, I have a lot of friends which are very, very far away, and maybe they are closer to me than people that live in Delft, for instance, okay? Of course, we can go on and we can talk about temporal dynamics differences between these two types of networks, how we deal with noise and uncertainty, scalability. You can imagine that a social network can scale up. If you want to add pipes to a water network, you need to find money, and it's going to be excavation. So, it doesn't scale in the same way. Okay, now, let's move into these networks. So you see here a computational model of a water distribution network. So this is drinking water, okay? You open the tap, okay? Now, we have, as you can see, lots of nodes and lots of links or edges. So node features, okay, let's talk more about graph machine learning now already. What are them? The type of node, for instance. So these are static features. It can be a junction where we demand water. It can be a reservoir, and by reservoir, we basically mean a source of water, an infinite source of water. And from a modeling perspective, it can be a tank that stores water. And gravity is very important. So also node elevation, the location literally of, the floor, for instance, at which we are, has an impact. So we need to take that into account. Volumes of tanks, if you have tanks, and so on and so forth. So these are some type of node features which are static. Then we have the dynamic features, which are usually the variables that we want to predict, okay? So we have pressure, which is very important, because if you have no pressure, you don't have any water. We have the concept of head. I don't know if you ever heard it before. Essentially, it is a measure of energy for a specific weight of water, and basically is given under certain condition, at least in this case, in steady state condition, we would say, by simply summing up, the energy that you have due to pressure and the energy that you have due to gravity, which is indeed the node elevation, okay? Then we have water demands, a very important variable that we usually specify at the nodes, and water demands drives the system, you can imagine. And then we have water quality parameters of different kinds. Now, for the edge features, again, we can have pipes, we can have valves, pumps. Now, valves and pumps, you've seen maybe plenty, like in your house or, maybe in your garden. Here, of course, we're talking about much different dimensions because we're talking about a network providing water to Amsterdam rather than your house. So these are important static features that we have at the edges. Then we have very important features related to the pipe geometry. So on top, of course, of the connectivity that you have, also the geometry of the pipe itself plays a very important role, especially the diameter and the length, because this determines, along with the roughness coefficient, the energy that we lose due to friction when carrying water from one point to another, okay? And this would be the head loss, which is a dynamic feature. As for the dynamic, properties that we can define on the edges, we have, again, head loss, as I mentioned, so how much energy we lose when water travels through a pipe, and flow rate, which is like how much actually water is going through the pipe. From flow rate, we can derive velocity, and also we can have water quality parameters and other things. Now, I hope this sort of like is less, let's say, I demystified a little bit what a water distribution network is. Then we also have urban drainage system, so the other side. And as I say before, we have stormwater sewers. They take, runoff generator due to storms and rainfall away from populated areas to avoid flooding conditions, as you can see here. Then we have wastewater, also known as sanitary sewers, wastewater sewers, also known as sanitary sewers. And as I said before, you can imagine, all the wastewater that we produce in the household, in an industry, in a commercial building, and this has to be carried away from the city after being collected using this network. Then we have the possibility of combined sewer system, as I mentioned before, okay? Now, I don't want to spend too much time also on defining the nodes and edge features that we have for this type of system. Some of them are the same, okay? At least those that you need to know for the rest of the presentation, I would say, and I guess Alex is gonna provide a little bit more later on. But in general, this system are actually more difficult to model than water distribution system. The dynamics are more complicated, and yes, so just bear this in mind. We don't have too much time to go into that, unfortunately. Now, what's next? Now we move to graph machine learning. We define these networks, right? Why do we want to use graph machine learning? Which is going to be this talk and the next talk, and somehow also your talk. But that's there's feature engineering in between. I think we do like a deep learning way, end to end. Of course, we are dealing with network. We want to exploit the inductive bias of this data being a network in itself or coming from a network, right? So we use graph machine learning. We exploit the beautiful, important information that we have on this structure, rather than giving it away if we use the type of machine learning models such as multi-layer perceptrons or random forest or extra trees and whatnot, and other types. So it should make a lot of sense. Okay. Hopefully I will convince you more if you in the next slides. Now, we want to do graph machine learning, so we can do some specific graph machine learning task in these water networks, regardless of whether we have water distribution or urban drainage systems. What are the most common? Okay, a very important one is state estimation. Okay, it can be, I think it has many synonyms from place to place, from application to application. But in our case, what we want to do is to infer the state of the network, meaning that we would like to know the head or the pressure and the flows everywhere in the network, ideally, from a few sensors that we can deploy in the system, okay? And this, usually we're dealing with continuous variables, so this is a problem of node or edge regression. Moving on, a very important task in the Netherlands, because the quality of the infrastructure is better than everywhere else in the world, I would say. But there are very advanced nations where we lose 30% of the water due to leaks, okay? And a lot of nations do that, which is terrible because, it takes a lot of energy and money to clean that water in the first place. And then, with problems that we're having with climate change is really something that we cannot afford. So leak detection, we want to, for instance, identify whether we have a leak either at the node, so the junction between two pipes, or in the pipe itself. Sometimes it can be a burst, really these pipes can explode. And sometimes they go unnoticed. So millions of euros are spent on this every day, unfortunately. So in this case, we want to find these anomalies, and we can do it in any possible way. We can do it with a classification at the node or the edge. If we just want to point out there is a leak, there is no leak. It can be like a regression problem if you want to go as far as quantifying the amount of water they were losing in this specific location. Okay. Now we can monitor the water quality. We can make forecasts on the water quality, and maybe we can also exploit time series data there. We can do asset maintenance. So usually we would like to know which components we want to repair or substitute, and this can be done, I think, with a node edge ranking. Where you basically prioritize. Usually it's a matter of prioritizing based on some criteria, which you have this amount of budget, which pipes do you substitute in order to improve the system, okay? So it's a huge variety of things, okay? I'm not gonna list all of them because it's really too much, but now we're gonna focus on this, meta modeling, okay? By meta modeling, and Alex will provide some extra details on this, basically we want to build a model of a model, and I'll show you why this is important for us. And what it does, basically, when we can use graph machine learning, because also the numerical simulator for solving this network produce graph data so that we can process with graph machine learning. We want to reproduce and generalize this physics-based simulation on a network with high accuracy and also considerable speed ups. Okay, so we want to run it 10,000 times faster, 1,000 times faster. It's also known as surrogate modeling. So maybe you heard it before, this idea of building a model from a model. Okay, now, I hope in the next slides, I will show you why this is indeed important. And this is the second and last part of my presentation. I hope it's not too long already. But, one of the goals of HydroLab, among many, maybe too many, is that we want to build transferable meta models for this water distribution networks. Okay, we'll unpack this in the coming slides. And this work is being mainly done by one PhD students who is affiliated with HydroLab, Bulat Kerimov, although he's doing his PhD in NTNU. Okay, so I'm presenting mainly his work. Okay, so if you go on any website of any provider of solutions, software solutions, sensing solution for water systems, it looks like we are working with the machines as sophisticated as Red Bull, like those the super fast cars. Like they show these amazing graphics with different variation of this AI generated drop of water with a wireframe or a pipe with a wireframe, as if, basically everybody's using AI and everybody's using AI to build these digital twins in the water sector, okay? You heard the word many times, right? If you look at this website, if you go to these conferences, it feels like this is pervasive, okay? We have so much data coming up from this network, very high quality data. We can do everything with it. We have, a sophisticated system, SCADA system that you don't even have in a shuttle, right? If you just look at this sort of advertisement, right? It is not true because, where is the data? I'm going to talk about this, and then I'm going to introduce why these simulations are important. Because if you basically hear what they say, it looks that, let's say this is a network, let's say in Delft, this is the amount of sensors that you have deployed, measuring, important variables such as flows in these pipes, water quality, in pressure in real time, okay? This is what you would expect if you sort of look into these web pages and you don't know anything about it. The reality is this: you have very few sensors. With a conversation with Elvi maybe two months ago, was it, at one of the other meeting, and then it was a little bit surprised of the density of sensors that would be indeed how many of these edges and these nodes we're actually measuring, okay? There's 3. I would say you'll be lucky if you have one sensor every 1,000 meters of pipes, okay? Usually, okay, not always the case, but yes. So I work with a lot of networks from the UK, one of the water utilities there, and what you see is that they usually have 3 sensors. They have a flow meter at the beginning, where they actually measure how much water is coming into the system. And then they have like a pressure sensor in the most important part of the city, so the city center. You really want to ensure that the pressure is good, maybe where the most populated area. And then you have another sensor at the so-called critical point, which would be where the pressure is the lowest. Because, you know, if it's high enough here, you can expect that at least customers are being, most of the customers are getting water. This is it, right? There's, you know, this is the reality, okay? And this is like UK. It's not where actually you have more need of sophisticated techniques to improve water management, right? So this is puzzling, but this is the truth. Therefore, what can we do, right? Well, we can use transfer learning, for instance, right? If you think about like a deep learning perspective, a machine learning perspective, whenever we have little data about a specific problem that we want to solve, okay, maybe we can transfer knowledge from a related problem, okay? I'm showing here this beautiful image generated by DALL-E, where you basically see GPT here, this foundational model, and then we fine-tune into ChatGPT, as you can see it with a little icon here. What I mean by this is that, you know, GPT, so this foundational model, see a huge amount of data, and then we can use little data for a specific case, because still the data seen to build ChatGPT from GPT is orders of magnitude less, right? A lot less. Maybe we can do this, okay? But where do we transfer from? Okay, so we can maybe transfer from, yes. Where do we transfer from? Meaning that, can we actually build a foundational model for water distribution networks? Okay, so this is the main research goal of this line of research that we are following at IDLE. Now, imagine we have a lot of different networks. Usually, we don't have data from this network, but we have sometimes calibrated models, calibrated numerical model for this network. So I'm a water utility, maybe I have only a few sensors, but since we're dealing with physical systems, there are laws, and then you can use, you know, these laws, you can solve them numerically, the related equations, I mean, and then indeed you enlist, you know, you can use the little data that you have for calibration, and then you say, well, you know, it's a physical system, it has some sort of reliability, although this is synthetic data most of the times, okay? But maybe we can do this. We can use a lot of different networks, either real, augmented, generated synthetically, run this model, gather data, and maybe do a pre-training of this foundational model. And then what we can do is also true that we have very few sensors installed in these networks. But if you think about it, so this utility in the UK that I mentioned before, it's true that they had only 3 sensors for each of their small networks, but they had 350, 500 of them, okay? So maybe we can pull all that information. Maybe we can use a model that is able to learn shared representations, right? And then maybe this model is pre-trained on the simulation that is fine-tuned by learning on sparse data, but coming from many networks. Pulling all this stuff together can help us actually deliver, you know, build a better understanding. I'm curious to see whether you think this is possible or not. But basically, that's why we need graph neural networks, okay? Because we need to learn transferable representation across multiple graphs. So we cannot do this with the old models out there. You know, we need to really match the structure of the data. And we can do this only with graph machine learning methods, whether graph neural networks or, let's say, maybe graph formers, which brings together graph neural networks and transformers. But this is the whole idea why we want to use this. And this is why we want to indeed do this meta modeling thing. It's not just an exercise. It's also a necessity because we don't have real data. So if we want to advance science, we need to rely on simulation. But it's actually a necessity if we want to move forward, at least in my point of view, this field of of engineering application. Okay. Now, what's next? Yes. So we have to learn from simulations, and in our field, we have, thankfully, EPA, the Environmental Protection Agency of the United States, developed very sophisticated, sophisticated enough models, which are, used by everybody. They're open source, and it's called EPA-NET, the one that we use for modeling water distribution network, and SWIM, the one that we use for modeling urban drainage systems. They share part of the code, but not all of it, because the equations behind it are only partially similar. Anyway, so this is how, we can learn from simulation. We have a model, we run it, we get data from it, we use it for training our graph neural network. And again, now I'm going to focus mainly on water distribution systems. As I said before, these numerical models solve set of equations. So what are the equations? The basic physics, let's say, behind water distribution system under certain conditions, of course, with some assumptions. We have the conservation of energy that we need to respect. By this, we mean that, the difference in the energy measured by the head, which is one of the variables that I defined before. You can think of it, again, as the pressure plus the elevation. The difference between the energy in these 2 points is equal to the head loss, the amount of energy that we lose because the water passed through the pipes due to friction. Okay, you can see here a simplified formula, which is empirical for computing this head loss. And basically, forget about this term, is not usually used. We have flow. This is the amount of water really passing through the system, the pipe, sorry. And then we have this coefficient R here, which is a sort of like resistance coefficient, which depends on the, let's say, roughness of the pipe itself, the material of the pipe, then the length of the pipe, the diameter of the pipe. Mainly these are the things, okay? So those that I just described were indeed edge features, which need to be used to compute this resistance coefficient. And then again is a function, as I said before, of the Q. Q is the flow, is the amount of water that passes through the pipe. And lastly, and I hope it's not too much, we have conservation of energy and conservation of mass. This means that if you take any junction, okay, any node, essentially, we have that the sum of all the water coming in and going out has to be equal to 0, okay? So, of course, if we have these strong laws, it's true also that we need less data. And it's also a basis why we can rely partially on simulations, okay? These laws are very well known, very efficiently implemented in the software. So that's why we want to go ahead with it. Now that you know this, let's define the problem. I hope, how much time do I have? 15 minutes. 15 minutes. Wow. Okay, then I'm gonna go slow. No. Okay, so let's define the problem. Okay, we want to learn from simulations. Which type of simulations? We start with steady state simulations, which in the case of the water distribution system can help us solve a lot of problems. It's very different from urban drainage system where, we usually don't have that luxury. But in the case of this, yes. So we use, what is the problem that we want to solve? Given inputs. Inputs being, of course, the network geometry and the characteristics of the networks, the water demand requested by all the nodes of the system, which can be estimated, usually, more or less, right? And then we need to also know the intrinsic energy that the water has, the starting point, which is basically the amount of energy that we have at the reservoir, at the source of the water distribution system. That's the source of water. In this case, let's say we have a water treatment plant, and then there is a big pumping station that pumps this water with a certain energy. The more energy that we have, of course, the more we can, deliver water far away in the network. But of course, if it's too much, then we break the pipes and it's not great. So that's another problem that we're not going to discuss today. So given these inputs, we want to determine the pressure, usually at all the junctions, ideally, and the water flow in all the pipes, okay? This is solving, we say, a water distribution system, okay, with simulation. Simplification, as I say, steady state conditions, and we don't have any valves or pumps or storage tanks in this part of the study because, we wanted to start simple. So this is one thing, but then we don't have to forget that we also want to build these transferable meta models, as I named them. So what we do, we run several simulations in ePNN on different case studies. Then we train a GNN to reproduce this simulation, okay? And since we want to really tackle this transferability to make sure that we can do transfer learning after it, we also need to see whether the GNN can actually be trained on multiple case studies simultaneously, so different networks, and is able to actually learn shared representation which are meaningful. Okay, so this is the problem that we want to solve. Okay, now the way that we tackle it, the first thing that we did is to use, I call it node-based GNN, but it's the traditional GNN that you might be familiar with, like graph convolutional network. And what we did, so this is the first of the paper related to this work. Basically, we utilize a encoder processor decoder. I guess you guys might be familiar with this standard architecture used a lot when dealing with the physical systems. So what we do, these are all the input features on top, of course, of the connectivity that is intrinsic, that is handled by the GNN because the processor is a GNN. But anyway, so these are the inputs. As I said before, reservoir head, so the energy at the starting point, nodal demands, which are driving the simulations, node elevation, because gravity is important. And these are for the nodes. For the edges, we have the length of the pipe, so it's a static feature, the pipe diameters, another static feature, and the roughness of the pipe, another static feature. Why this? Because this is important to compute the head loss, which is going to then affect the energy that we have in the system and have consequence, of course, on the water that we can deliver. So we encode this information. We have some first stage hidden representation that we elaborate using a processor which is made of n layers of a graph neural network. I think in the first paper, actually, we use a chatcom. So it's more like different neighborhoods that we can go up. But of course, it's equivalent to having, GNN with the graph convolutional network, more or less, with only one op, so only looking at the direct neighbor and then stacking them on top of each other. We process this hidden representation. We have a feature-rich towards the end, of course, of the processor a representation that we need to decode in order to obtain, in this case, the pressure at all nodes. Then from the pressure at all nodes, we can derive the flows. Okay, so this is what we're going to show now. So we use this model and different parts, so not yet the results. So this is the encoder, is a shared multi-layer perceptron. So we work on each pipe, we take the features of each pipe that I mentioned before. We take also the feature of the two nodes, the beginning and the end of the pipe. We concatenate this feature. We pass them through an MLP. We create this hidden representation that you can see here. And then we're working on the nodes. So what we do, basically, we aggregate this information at each node by, of course, pulling together, averaging together the hidden representation that we have for all the edges going into this node. And we create, indeed, another hidden representation. And this is the, let's say, the starting point for our GNN layers. The start, of course, with message passing, convolution, aggregating this information until we reach, let's say, a final representation that then is going to be decoded by another MLP that works at the nodes that I'm not showing here. Okay, so this is the model that we used. Now, the result that we got, so we try on these 6 networks, first of all, on a case-by-case study. These are standard benchmarks that we use in the field of water distribution systems. We have networks going from 55 links, I would say, up to 1,000, this one here. And what you see is that it's not good. We were not happy with these results. You can see that, we compare against an MLP, we do a lot of hyperparameterization. And what we find out is that we do pretty well for some cases. This one here is quite interesting because it's a very looped, system. But on average, the MLP does a little bit better, and it's much faster despite being bigger. Much faster because when you run on GPUs, MLPs, much more optimized than running a GNN, as you may know. So not great. And also even the MLP sort of like didn't really do that well. You would like to have this R square, right? This should be around ideally 1. But if you start seeing values which are below 0.8 or below 0.9, then I'm not sure if you can use it in reality. Okay, it's not promising. Okay, so this was not great. So let's say, well, let's put all the networks together. Let's train a GNN on it. Let's see if at least we can actually learn some share representation. And no, I mean, yes, not so much though. So what you see here, the blue crosses are basically the results obtained in different runs of the MLP. The orange one are different runs of the GNN, so for which we computed the values that you see before. And then these 3 other dots here basically are the performance of a GNN trained on all the network. This is, of course, always test results. Using like a different data set that we tweaked to balance a little bit, the representation of each individual network. So we don't really get very good result, but we start seeing that, at least, if you start feeding more data, and if this data is more balanced, that maybe doesn't represent network which are smaller, so with less nodes, and since the loss is computed at every node, they end up being less represented. There is some room for improvement. So this gave us a little bit of hope that actually we can move forward. Okay. But how did we move forward? We completely changed the architecture. Like we moved from a node-based, let's say, GNN, which is a typical way of doing it. We switched things around and we start focusing instead on the edges. So before we wanted to predict pressure, which is a variable at the edge, and then reconstruct the flows. Now what we want to do is actually predict the flows and then reconstruct the pressure. And we will see why we had sort of this intuition. So what do we need to do though to operate on the edges? One main thing is that, as I said before, the driving force in these systems are 2. The main one, the 2 main ones. One is the energy that we have at the reservoir, the source of water, and the other one is the amount of water asked by each individual node. Okay, so these are variables that at the moment are defined on the nodes, right? So if you want to switch the focus to edges, we need to do something there. So what Bulat did, basically he added virtual sinks, let's say, and sources to the network. As you can see here, so this is the original graph, right? Then to each of these nodes, we add, let's say, either a sink in most cases or a source in this case for the reservoir. This one here is the reservoir. So basically now we have this node here, and now the water demand is specified as the water flow that we have, in this pipe. So we create these artificial pipes, let's say, that don't exist, and we specify the flow of water in this pipe to be equal to the original nodal water demand, because they're equivalent. A nodal demand is also a measure of flow, is a volume of water per unit of time. Okay, on one end. And what do we do with the reservoir? Basically, especially in the case when we only have one source, that you start from the assumption that you are always able to meet the demand. What this means is that the sum of all this is essentially the flow in this additional pipe here. It has to match, okay, if there is no leak. So we're still under certain assumptions, of course. And by doing this, then we can actually operate it at the edges. And why did we do that? Because, let's going back to this physics, you can see that Q, which is flow, which is this variable that we want to predict now, features on the law of conservation of energy as well as in the law of conservation of mass. So heads are only here, right? So it doesn't look like it's the most important variable in the end, because, since we are modeling a physical system, it makes sense to also exploit that other inductive bias, which is related to physics. And in this way, we say, okay, look, it seems to be more important to look at the other way around, okay? Actually, there is also, and I invite you to read the paper, which is actually here. By doing these convolutions now on the edges, basically we enforce somehow this conservation of mass. So if you look at the formulas there of the paper of Bulat, there is an even more strong reason behind why we are using this. Well, the paper is in review already for 3-4 months, so hopefully you will be able to see it soon. Anyway, what happens when we do that? Many more networks now, like we have 10 before we had 6. First, we checked, the performance of this new ENN, like edge-based GNN, on 6 of these networks. And all of a sudden, we start seeing much better results. So you can see on the left and on the right, the R squared, that we have on the heads, on the prediction of the heads, which are reconstructed from the flows. And here we're talking about the flows. So we have an improved version of a GNN that we use. You can see these lines in pink against this new edge-based neural network that we created. And you can see that this edge-based neural network, it performs always well, especially for the flows. And also it is much more robust when it comes to network and when it comes to data set, which see a lot of variability, okay? So you can see maybe it's not close enough, but when we have the continuous lines, basically we are using the same network, the same edge attributes in the network, so the network never changes. We're only changing the demands, okay? In the other case, the one you see with this dashed line, we are actually changing a lot all the pipe parameters, okay? So there's much more diversity. So this to check for robustness. So we see that this network, the ENN, performs better, and it's actually also much more robust, which is promising. But most importantly, we ran this other study on transferability, this other experiment, where we train on these 6. Yes, we train on these 6 networks, which are also augmented with data augmentation. And then we test on these other 4 networks in a zero-shot fashion. So we don't do fine-tuning. We just learn here, and then, we transfer there. And the performance that we see are pretty good. So we have with the zero-shot generalization, we have R square of up to, everything is above 0.8, more or less, okay? So it's a huge improvement with respect to what we had before, okay? But just switching to this new type of architecture, which of course is very promising, I would say. Of course, as I said before, they work better, they have much better transferability, they enforce physics better. Also, we do have speed ups, which are not great yet, but they can be improved if we then, instead of having this intermediate step where we predict heads from flows, we do this together, but this is something we'll do later. So all in all, basically we believe that there is room indeed to build these meta models, transferable meta models using GNN, because we only use 6 case studies and already we're doing well. So imagine if we scale this up, to like 1 million of different networks, which we can always generate. And then hopefully we have some enlightened water utility that give us the data to fine tune it further using whatever data they have. Yeah, thanks for listening, and sorry for the fire alarm. Thank you.